reasoning machines all day. And the question is, what about the reasoning part of it? How good is reasoning? And how far have we come? How much can we get out of a model that's really just good at completing sentences? And how much do we need to push beyond that into models that are actually designed from the beginning to do thinking, and thinking at an advanced professional level? So I am thrilled to have two leaders that are going to join me on stage who are pushing the boundaries of this and, thinking about the future of thinking. So please welcome Carina Hong and Byron Cook to the stage. Now, Carina Hong is, come on, sit in the middle, or whatever. So Carina Hong is Madrona's newest CEO as of yesterday. She is the founder and CEO of Axiom Math. They are building new advanced AI reasoning models that are trained on mathematical proofs. And Byron Cook is a VP and distinguished engineer at Amazon. And he leads the automated reasoning group at Amazon, which applies formal verification for verifying things like billing systems and security and the integrity of models and the accuracy of output. So it's going to be a really fun discussion. Thank you, Byron and Carina, both for joining me.
Thanks for being here.
Thank you.
So help me orient. We're in a world where we've been talking about reasoning machines all day, and actually the models that we have that are sentence completion, they seem to reason, they seem to think. So why do we need to be talking about next generations of reasoning when we have pretty amazing models already? Why do we need to be doing advanced, ambitious new moonshots?
Yeah, for sure. I think currently reasoning models are getting really good at pattern matching and matching specifically for human preference. They are trained on chain of thought data, which is made by experts, lines and lines of chain of thought to approach a specific problem. However, there are certain areas that human preferences don't cut it. Those areas require objective truth, absolute right or wrong answers that you cannot get right or wrong because some humans prefer it more than others. And one example is mathematics. The other example are engineering, coding, quantitative finance, etc. Those more quantitative scientific areas. And reasoning models fall short at that. For example, if you ask a model to approach a really difficult high school level mathematical proof, it actually cannot generate the correct intermediate steps. And that's a really sharp kind of contrast with some other domains that it achieves expert level performance. And there's also a question about scaling, which is currently we see them doing okay, but as you try to hill climb in these domains, it gets harder and harder to make reasoning models continue to work. Because currently the way to give them some signals about whether they are getting it right or wrong is by 10,000, 100,000 large language models, agents voting yes or no. And that gets extremely expensive as you try to scale up to harder and harder difficulties in those domains. So verification must come in, which is objective truth, right or wrong. I'll leave it at that.
Byron, what do you think?
So I'm coming in, I've been at Amazon for 10 years applying proof tools in AWS infrastructure and also for customers. And so I come at it from the other side where an incorrect answer is a crime. Right, so you can't answer, you can't give the wrong answer. So we apply mathematical logic to $100
billion of billing in a year. We got to bill it right.
Exactly. Yeah. The cryptography needs to be correct. The virtualization needs to be correct. The storage needs to be correct. The interpretation of the policies needs to be correct. So that's kind of where I'm coming at it from. And then, but the sort of challenge for us has been that the tools that you use to achieve that 100% correctness were harder to use and required PhDs. So for me, what's quite exciting about the recent trends is that suddenly these tools, in combination with machine learning, become actually potentially much easier to use.
Can you say a little more about that? One thing that's amazing about this field, applying reasoning and formal verification in technology has been around for a very long time. I think even before you got started with it, which was some time ago. But it has been an artisan craft, and it required experts to verify line by line that this airplane autopilot system is going to work as designed. So we couldn't use it everywhere because we had to use it only where we could find the resources to do it, justify the resources, find the people. So what changed, Byron?
First of all, as computers were networked and as society began to take more dependence on computers, the need for that work became more and more important. So as people moved to the cloud, for example, proving the correctness of the cryptography became the reason that customers actually came to AWS. Proving the correctness of the policy interpreter became the reason that people came to AWS, and so it helped AWS grow. It helped customers move, and that became an area of importance. And then we in AWS have been able to make the tools more and more usable. But also, there's been other advances, like, for example, the REST type system is essentially separation logic combined with really good error messages. So there's been effort there, and then more recently with machine learning tools, that's really been a breakout. The other thing is to keep in mind is that the models are often trained with data from proofs, either synthesized or discovered, and so the models are actually often quite good at using, for example, the lean theorem prover, and so that combination of the human and the AI tools understanding lean or Isabelle makes the tools much more approachable.
I want to put a fine point on this because it's something that took me a while to get my head around. Chasing bugs, chasing incorrectness in something like a billing system or a security system, for a long time, or even like an autopilot system, was a bit like being a goalie, where you're just trying to stop every vector of something that could go wrong, and trying to think of all the things that could possibly go wrong and knock them down one by one. And you're using a word, proof, which is a big word, which says it's not just everything that I've thought of that is going to break, but this will not break. This works, and I can prove it. Can you say a little more about that?
So you can identify properties that you want to hold in the program. So for example, all data at rest must be encrypted, or there's no memory corruption errors, or strong consistency is actually guaranteed as opposed to eventual consistency. And then up to that property, now you can prove using techniques like mathematical induction, which is the same technique we use to prove the Pythagorean theorem or the four-color theorem. And so it's the sort of foundation of how we know what's true of the infinite. It's how we know there's an infinite number of primes. It's the foundation of truth in our society.
And so when we say proof, we mean it in a mathematical sense, that yes, your AWS bill is going to be right.
Yeah. What's amazing now is with the world and society, the usability of generative AI means that people have discovered this problem too, and so they are trying to remove the socio-technical mechanisms with, agentic tools or chatbots, and that notion of the answer is wrong. How do I know the answer is right? Can you give me an argument as to why the answer is right? Is something that the world is sort of waking up to the importance of that, whereas before it was quite an obscure area. Yeah.
So Carina, there's something we've spoken about a bunch of times, and I want to sort of share this with the group, that there is a market for reasoning on this earth, in this world, and there is not enough really sophisticated reasoning to go around to solve the important problems that we face. How in the world is that true? What does that mean? And what does it look like when we go from a world of scarcity to abundance in reasoning?
Yeah, 100%. Double touching the point Byron was making, which is that for a lot of the programs, we currently have an output and a property. Large language models are good at generating the output. They're unable to prove that this output satisfies that property. So that link, critical link, is missing. And that's why proofs, in addition to computation, becomes extremely important. Mm-hmm. Only when a model is trained on proofs and similarly executable programs, you can know for sure it's right or wrong. The really technical breakthrough happened in formal language called Lean, and similarly like Isabelle, and there are a few variants of theorem proving languages. They turn mathematical proofs into computer programs by Curry-Howard correspondence, which is a scientific term. So that means for every single math problem and the proof associated with it, I can turn it into a computer program, which I can then click it and wait for it to run. After it finished running, I can see either a check mark, which tells me, congratulations, it's good, proof is good to go, or an error message, which I can then feed it back to the model to help it to revise and adjust for the correct answer next time. And then it keeps doing so, and eventually I will get a check mark, which is, wow, congratulations, this proof is actually logically sound. At Axiom, we are trying to solve the problem of the scarcity of outlier human reasoners. If you think about the history of scientific discovery, and I keep thinking back to some mathematicians' lives and their legacy. Ramanujan died, I think, at the age of 32, and before he died because of starvation and ill health, he had tons of notebooks, and those notebooks have formulas in it that took subsequent mathematicians, I think, decades, if not centuries, to prove. And I also think about Galois, the guy who really pioneered group theory. I mean, he died incredibly young, I think 22, because of a duel for a girl that he loves. These are the kind of human outlier reasoners that the society lacks for true scientific breakthrough accelerating to market applications to happen. If we think about abacus giving rise to accounting, integrals, calculus giving rise to thermodynamics, mechanics, and then the Industrial Revolution. We think about Babbage engine, which is a mathematical tool to make log tables faster. That's the prototype of computer, but there's a significant time lag of 200, 300 years. AI compresses everything. You can consider what happens if billions of AI mathematician agents go to every single complex system that is currently not understood and work with applied scientists, domain experts in these fields. In chips, for example, have a theorem prover help formally verify chips, to work with people who are the best software engineers, have a theorem prover help formally verify code, work with people who really understand the economics. I mean, quant trading has previously been really restricted to the domain of high frequency or some mid-frequency quantitative trading. I was previously working at XTX Markets, a leading hedge fund. But really, why has anyone not thought about combining those really outlier quantitative methods to some more traditional, say day trading? What happens if you have an AI Terry Tao, AI math whiz work with every user on Robinhood? What happens? And I think that's the question that we need to ask ourselves about is when we enter the era of mass intelligence and mass outlier reasoner grounded by verification, because we couldn't afford to have really these billions of agents that we don't really know the answer being right or wrong. Just, okay, I see a 1,000 line math proof and you tell me that I have no way to check it. Surely I cannot have humans check it. That's extremely expensive when it comes to scaling. But once you have these thousands of math proofs and you know that there is no chance it's incorrect, it's good for use, that's incredibly impactful. What's even better is in an era of agents, I can make sure that the stuff I pass from agent A to agent B is correct. I can't really afford to pass incorrect and lousy work to my teammate during my legal training at Stanford Law. But what happens if you have verification, if you have agentic workflow, if you have the ability to conjecture and generate new problems to think about, and then have the verifier to try ground it and prove it? This sort of self-improving AI, recursive self-improving loop, I think that is the amazing future that building a reasoning engine at the model layer helps unlock.
So let me try and make this really tangible. Take me back to your work at this quant fund, XTX, which hires people who are really, really good at math and basically hires every person who is good enough at math that they can find on Earth. Not enough people that they can find. And there are other fields that do this too, by the way. But let's focus on one field in one firm. they're in a world of scarcity of reasoning. What happens to a place like that when they can suddenly turn on more reasoning, like a tap of water, like a tap of electricity?
I think the future in these players is quite interesting. There are different dynamics with each of these players. So imagine you are a firm that actually doesn't have access to the top MIT, Princeton math PhD students. You just do not have the talent pipeline to employ these extraordinarily bright young minds to be quant traders. Suppose you are a hedge fund in a market that's total trading volume is quite low, which means low-hanging fruit is everywhere, like really not so hard to derive alphas are everywhere. You just don't have the talent to help unlock it. I think that's really meaningful for these players, first of all. Second of all, for these players that have already amazing talents, then they have these AI mathematicians to collaborate with. They don't have this sort of problem where I think as some other hedge funds, which is, I have never have worked in, but I just read it from all sorts of books, where different desks have different trading strategies. For example, it can be quite isolated to develop, one thing that you own, full end to end, and you have these AI mathematicians that's bound to be correct to bounce ideas over, and you can think of talking to the AI as your tea time, generate really interesting quantitative methods with the AI collaborators. So having this sort of strong supervision from the existing amazing talent outlier human reasoner is going to only accelerate the discoveries and breakthroughs in the algorithmic, in the scientific sense.
Yeah. One thing that I think we've seen with the first waves of Gen AI is that the marginal cost of creativity and experiments is dropping. We saw this in the cloud, Byron, and AWS, when the marginal cost of experimentation for a cloud developer dropped, and I could run an experiment much faster without ordering racks. And now I can do that with all kinds of creative fields. And I think to your point, Carina, if I'm now doing it in fields where being right super matters, be it because I'm betting billions of dollars, or I'm, people are going to get hurt if I'm wrong, or any number of reasons, you start to get to that next level if you can move from a world of reasoning scarcity to reasoning abundance.
Yeah, for sure. I mean, Jevons paradox tells us that when the price, when the cost of the tool becomes lower, there will be new market cases, use cases to be unlocked. And I think really we are in an era where Jevons paradox is our opportunity. What happens if every cloud compute provider can afford, say, Facebook engineers that currently paid $2 million each year to work on the routine, mundane like IT optimization ticket task? Like just think about what that means. And what if a hedge fund, right, in a trading volume of only say 8 million each day can now afford a trader, an AI trader that's as good as those being paid currently 20 million each year as a starting salary in certain quant firm places, as this does happen, to afford these AI mathematicians, but only pay them $5 each hour.
So help me, I'm laughing with maybe some other people at the term only 8 million. Help me understand how broad is the application of reasoning with math? Is this about creating more math for its own sake, or there was huge generalization here, and I think that's counterintuitive, at least was for me until you guys explained it to me.
There's a little bit of survivor bias going on because I'm pulled into the conversations where it's needed. But from what I see, like I've worked in reasoning about genetic regulatory pathways, railway switching, safety, microprocessor design, operating systems, virtualization, storage systems, networking. Any question where there's a system and the system is evolving, there are questions around termination, around reachability, and most of those turned into questions about unbounded, infinite, or intractably large problems. You've also got, like, we haven't really we've talked more about lean, but there's also the propositional satisfiability solvers and SMT solvers, which handle combinatorial reasoning. So you've got the problems are typically NP complete or they're undecidable, and these tools, eat those problems up for lunch. So many problems are translatable to state space reachability or termination.
Okay.
Yeah.
So if I follow on this line, and I have tools and techniques that are broadly generalizable to be really, really powerful, super intelligent brains that we can turn on like a tap. Each of you are leaders who have to straddle two lines because you're doing advanced research to push the frontier. And I know, because each of you told me, that you're also pushing really hard to apply this and actually put it in front of customers and make it land as opposed to stay back in the lab. And so maybe you can talk about kind of the leadership experience of that and how you balance your resources and your team and even your culture about the relative importance of awesome math and code for its own sake versus the impact it's going to have for customers.
So Strachey, who was a contemporary of Turing and founded the Oxford Computer Science Department, says that the division between theory and practicing computing is injurious, that the theoreticians essentially don't know what problems to work on, and the practitioners don't have a grounding in what they're doing. So what I have found is that, even when I was in Ivory Tower, Blue Skies research labs, that those who ground themselves in customer problems were the most successful because they were able to extract out the theoretical challenges. So for example, I worked on termination proving, driven by the observation that device drivers need to terminate, and also genetic regulatory pathways need homeostasis. And that is the same problem. So what I've done with the scientists that work at Amazon and in my career is to help people see it's an and, not an or, and to kind of to work both in the theoretical and the applied. The other thing I'll say is that one of the big challenges for this space is figuring out what it is you want, what should be true. So like I can systematically remove incorrect statements from a chatbot about the Family Medical Leave Act. But first I need to encode what are the rules of the Family Medical Leave Act. And to do that has typically been a challenge. So you end up spending a lot of time identifying what is the correctness of the AWS IAM policy language. What are the semantics of AWS VPCs, right? What is the semantics of Rust precisely? And that actually turns out to be surprisingly hard to do. And so to make practical progress, you have to kind of drive on that and sometimes make some compromises. One of the very nice things about the rise of generative AI is that these tools now can help you do that. So you can get them to help translate the natural language into logic and help you figure out what the logic means and figure out what it is you want to try and prove, and then maintain that over time, right? So you might maintain your formalization of the Family Medical Leave Act, and then as you deploy your agentic system or your chatbot based on that formalization, over time you might realize you got it slightly wrong and fix the formalization.
Got it. Let me turn this upside down before I bring it to you, Carina. How do you, Byron, explain it not to your team, who are going to want to know, how much should we be doing awesome research versus applying it? How do you explain this to Andy and Matt Garman about why in the world we should be investing this level? Because Amazon has been investing bigger and heavier and longer in formal methods and automated reasoning than anybody. And how do you explain why that matters, why that's so important?
The customers did it for us. So I was in the Blue Skies research lab, explaining things on a technical level in the past. And then when I joined Amazon, because I'm in New York City, I was pulled into conversations with financial services. Mm-hmm. When they discovered the work we were doing, they went and drove that discussion. Actually, they went to other customers and helped them appreciate the importance of the work. And they drove those discussions with Andy and so on.
Because they said, hey, look,
this is why we're going to move to AWS.
This is why we're going to move to AWS.
Yeah. Orders of magnitude workload, because now we understand that the cryptography has been proved correct. We understand the story around the virtualization. We understand the durability story. And this is why we're now comfortable moving our workloads over. And this is something we would never be able to do ourselves.
Because previously it was a list of things that might go wrong, crossed off the list. And no, Byron comes with a proof that says, no, seriously, we mean it.
Yeah, and you can also, it's a transparent way of describing to your auditors or to countries why certain things are impossible, right? You can
Cool.
provide a proof in mathematical logic without showing the data why data can't flow to certain places, and that's important to certain governments and customers.
Got it. So Carina, if I bring it to you, you've assembled a team of mathematicians and developers and researchers who like things that are awesome. And they want to do advanced cutting edge work and push the boundaries of reasoning. How do you set the point with them that we're going to apply this? And how do you set that balance, and how do you calibrate what inputs they're getting?
For sure. I think, this is actually a contrarian panel in a way. The call to action of formal methods applied to reasoning is not something I think that has been talked about and appreciated enough. And I have these challenges when I'm talking to investors, when I'm talking to talents, when I'm talking to my mom. So what exactly are we doing? And so we launched yesterday morning. Axiom came out of stealth. There's a Forbes article, you can read about it. We're building a self-improving, super intelligent reasoner, starting with an AI mathematician. So all these terms are contrarians. Like VCs don't know why they should invest in an AI mathematician. People don't know what does self-improving AI mean, besides that being in the first paragraph of Zuckerberg's personal superintelligence memo. And what is superintelligence anyways? I think we know for sure this technology is likely to work, more likely than not. And this is the reason why Axiom has been a hiring magnet. I think we are able to attract talent at the caliber of Facebook, AI's directors, and other companies' senior tech lead managers level, because they believe in the mission. They believe in working for a company that is developing the next step function change of technology. That is, if you compound formal verification, like we talked about, with better and better learning and search, then you really have a decent shot toward superintelligence that is defined as a model that can generate new problems for itself to work on with 100% correctness, and then generate more interesting, harder problems based on how it did last time. So I think the technical vision being sound, and that really helped with hiring. And in terms of, say, justifying to investors, customers, I think people are seeing three things coming together right now as consensus in the AI field. One is the reasoning models on the informal reasoning side have gotten stronger and stronger as a good backbone of building things on top of it. Second is the formal verification tools like Lean 4 have really been widely accessible, and so many Lean developers in the world are trying to build tools within Lean, or trying to expand the mathematical library and the CS library in Lean, and that has really become a phenomenon from a subculture. I mean, back then, I think 2 years ago, people who are Lean developers talk to each other. It's almost like, wow, I can't believe you are also doing this. This is a language that no one has heard of. But now it's, wow, we have a vibrant community of Lean users. So that's the second part. And the third part being that code generation have got extremely, extremely strong. Reinforcement learning applied to a verifiable domain is going to have performance gain that has shown in coding. And now by turning math into programs the first time, we can see reinforcement learning being good at math, logic, and reasoning. So these three trends powerfully come together, which is also the hiring thesis at Axiom, which is we need experts from three fields: from AI, applied AI deep learning, from mathematics, and from programming languages. Really, the combination of these three fields, and math obviously include both mathematicians and people who are Lean experts, who usually are mathematicians. So these three pillars is what it takes to build an AI mathematician as the first step to a super intelligent reasoning engine.
Got it. So we've got time for, I think, one question from the group. Who would like to hear from Carina and Byron? Yes, sir.
Yeah, it's fascinating to hear from you. So Carina and Byron, so with your outlier intelligence or superintelligence, what problem domains are you most excited about going into or solving problems? So it will be good to hear some examples of that.
I'll characterize the solutions where the space of satisfying assignments is very sparse. I appreciate that's probably a mathematician's way of describing the space, but when you have in biological systems and in physics and in programs, security, there are many programs that are incorrect and buggy and insecure, and very few that are secure. Yeah. And so to balance that, the different dimensions of privacy, sovereignty, security, availability, durability, and to meet all of those and to write down those specifications and then to find the programs that meet those specifications, and especially in the enterprise, that becomes increasingly sparse. And so I think the generative AI combined with the formal reasoning, neurosymbolic AI, I think there is really great. An example which would not be great is poetry, right? So I don't want to, I don't think that formal verification is going to be especially good at proving the correctness of a song, right? or a poem or something like that. So there's a spectrum for sure. But those areas where very large amounts of money is on the line, people's safety is on the line, security, privacy, sovereignty, and where the consequences of getting it wrong are pretty bad is, I think, the area where the methods are best fit.
Yes, I'm most excited about, it's really two parts when it comes to go-to-market, which is scaling formal reasoning in all existing market, like really looking around the corners, because we're talking about things that previously people kind of just accept, that the verification of a protocol could take 3 years, and now you're telling me, wow, it takes 2 weeks. Like what happens then? So I think really scaling it out by looking around the corner, and really that depends on collaboration between various industry experts. And we really appreciate customer inbound, which is, hey, you have this problem that you try to solve, and I think maybe formal reasoning is helpful. I don't really know, Carina, and then we can talk. And these conversations starting are really just generally promising signs that perhaps we can find a corner that's immensely valuable. And then the other part is once this mass intelligence era is unlocked, what does it mean for unlocking new markets and use cases? That part requires some part of dreaming about the future. Like I read a lot of sci-fi novels, and I was asking sci-fi authors this question: is what does it mean? And no one really could quite figure out exactly what that is going to mean. But that part is definitely something I'm extremely excited about. On the technology side, I want to emphasize that technology is extremely hard. We have a data scarcity problem. If we think about how many tokens of Python code there is on the internet, it's probably about 1 trillion. I think that's a safe estimate. And how many tokens of Lean code, the programming language for proofs? Probably 10 million. So that's a 100,000 times data gap. And we know that scaling works really well in AI. So when your data is scarce, that generally means the technology is going to have a cold start problem, which is why we are taking bold data bets by various methods of automatically not relying on human experts to write the Lean code, but to automatically, synthetically generate high quality, extremely interesting in terms of helping model training data. I will highlight that as one pretty difficult technological problem.
Cool. I think we can keep this going for a long time. I'm going to be thinking about what is the most true and correct song that I know. We can leave that.
The Song of Pi, perhaps?
Good. So anyway, that's the discussion for later. But thank you so much to Byron Cook and Carina Hahn. It's been a fascinating conversation. Thanks, everybody.